right? Look at his handwriting. I mean, maybe this is too much, but in most of the cases, his handwriting is fine. But just occasionally, you can meet the real artwork look like this. I mean, my classmates and I spent 10 minutes to figure out what it is. It turns out it looks like the plasma. I mean, it's quite crazy. So if you really want to read Professor Diamond's lecture notes, make sure you have a minor in archaeology. Okay, and some other contents of this talk come from the ancient review papers. For example, this is a screenshot of Tang's review on ballooning mode. Just like other old classics, it has many useful physical insights, but I mean, look at the pages, number of pages, 73. I mean, it also has many algebraic derivations. I mean, so the useful physical insights were buried in the algebra. So it's pretty hard for people, especially for beginners, to extract these physical insights by reading these ancient classics. So today, my task is unearth the physical insights buried in algebra. So here comes the introduction. I mean, in this program, we have listened to many talks on plasma physics and nuclear fusion, and we have seen vivid realizations of a plasma turbulence, Lorentz flows, and staircases from large-scale, high-resolution simulations. In these simulations, the setup could be very complicated to simulate the reality. For example, we have very complicated magnetic geometry and boundary conditions and the profiles, right? But at the same time, the models we are familiar with are quite simple, like the Haskell-Mima equation. We have very uniform magnetic field, a very simple density profile. But there is a gap between the complex reality and the well-known simple models, right? So, and especially the geometry effect, including the magnetic shear or velocity shear, has very significant effects on the plasma dynamics in tokamak, right? So, if once we see these realizations, I mean, for some people, we don't have the useful theoretical tool to interpret this phenomena. So we need the theories involving the geometric effects. So today, the main target of today's talk is to give you an introduction of the theories involving the geometric effects. Here, I need to clarify that geometry in this talk refers to the magnetic configuration. We mainly focus on the magnetic shear and the toroidicity effect in the tokamak. So this is the outline of my talk. Basically, it's divided into two sections. In the first section, I will focus on the periodic cylinder. Think of you can imagine that we cut the cylinder and straighten it into a periodic cylinder, and so in the first section, the toroidicity effect is excluded, and I will start with the definition of the resonant surfaces. The reason I put it at first because the resonance is very important. It pins the turbulence in plasma. And then I will show you how the magnetic shear can stabilize and localize the plasma modes by using the idea of line bending and energy principle. And then I will show you how resistivity break the frozen-in law and leads to the resistive interchange. I mean, as we can see, the resistivity will restore the plasma instability. However, at the same time, even though the plasma mode can continue growing due to the resistivity, it's still very localized. So it's good if we look at the wave packet of these localized modes, which has a much broader mode structure. So this brings us to the quasi mode. Another reason I want to talk about the quasi-mode is it can serve as a bridge to the toroidal world, as a connection between the cylinder world and the toroidal world. And so after we'll go to the world of torus and talk about the ballooning mode. The two conventional methods are introduced. That they are block eigenmode equation and the ballooning mode representation. So after you might get tired of the linear mode one after another, I mean, because we just go through many modes. But after the linear theory, we will talk about nonlinear part. I mean, this is beyond the linear theory. So today I selected 3 topics: the shear enhanced correlation, and the nonlinear coupling, and indication for the avalanche. This nonlinear aspects of this talk are very, very important. So please take care of them. And I want to say in this talk, I will mainly focus on MHD because it's simplicity and attractability. But I should also emphasize that most of these conclusions, especially the qualitative conclusions, are generic and not restricted to their applicability are not restricted to the MHD. So in case you get lost during my presentation, I like to summarize the messages you need to get after this talk. I mean, there are 4 basic elements in my talk: resonance, shear, and wave packet toroidicity. So after this talk, you will see how these 4 elements modify the linear plasma mode, how they affect the nonlinear coupling, and how the emergent state, the avalanche, is formed with the presence of these 4 factors. As said, after this talk, I will give you, if I have time, I will give you a sad story about the velocity shear. Since this talk, I mainly focus on the magnetic shear. And another thing is, you cannot listen to this talk for free. There is advertisement time. I mean, since this, so I will, during the advertisement time, I will briefly introduce my own work, how the stochastic magnetic field modify the plasma dynamics. Okay, here comes the show. In a periodic cylinder, we can write the plasma mode into this form, right? E to Im theta minus n phi. So the d phi over d theta defines the mode pitch, which is also the ratio of m to n. M is a poloidal mode number, n is a toroidal mode number. But in the tokamak or in the periodic cylinder, not only the mode can wind, the magnetic field can also wind, because this is the equation for the field line. We can see since the poloidal magnetic field is also a function of radius, I mean the field lines with the same pitch can define the magnetic surfaces in tokamak, and on different magnetic surfaces, the magnetic field pitch is different. So we can see the QR is a function of R, which indicates there is magnetic shear in tokamaks. So the important thing is when the field line pitch equals the mode pitch, and that is Q equals M over N, we can define where the plasma mode and the magnetic field are represented. So because we're talking about the periodic, M and N are integers, so the Q is a rational number. So sometimes the resonant surfaces are also called rational surfaces. Look at this picture. This is just a cross-section of a poloidal cross-section of the tokamak. For resonant surfaces, if you can think of this picture as a concrete map of the field line. For resonant surfaces, the field line will each time the field line crossing this poloidal cross section, it will leave a point on this cross section. As we can see, if Q equals 3, then when the field line passing this cross section 3 times, it will go back to the original point. However, for non-resonant surfaces, since Q is an irrational number, it can never go back to the original place. However, I'd like to, you may ask why the resonance surfaces are so important, why I spend so much time explaining its definition. It's because on resonance surfaces, since plasma modes and magnetic field are resonant, the parallel wave number of the plasma mode along the mean field line is equal to 0. So why key parallel equals 0 is a big deal, because it can minimize Landau damping. Recall the Landau damping requires the resonance between particles and waves. So the phase velocity and the particle velocity should match. However, if k parallel equals 0, the phase velocity will diverge. So these two velocities cannot match. So on resonant surfaces, we can minimize the Landau damping. At the same time, at the resonant surfaces, we can minimize the line bending, which is energetically unfavorable. Many of you might be familiar with the energy principle. Basically, it tells you if there is a perturbed displacement, how the energy of the total system change. So delta W is the change in the total energy. So as we can see, the first term is always positive definite. It's proportional to the B0 squared and K parallel squared. So in the limit of the low beta, this term could dominate, and K parallel squared equals 0 means this term vanishes. But if K parallel squared is not equal to 0, which means there is a very strong stabilization effect, so which can stop the mode growth. So here we can draw a conclusion that resonant surfaces are ideal habitats for modes and islands and some other for some other things, because just like if you are a mouse, you prefer living in an area where there's no cat. Right here the plasma mode is just like a mouse, and the Landau damping and the line bending is just like a cat. So since the plasma modes prefer staying at resonant surfaces, we can say the resonance pings the turbulence. Modes live on the resonant surfaces.
So it depends. You said you do an HD, so have you specified
in this part, we focus on the periodic cylinder. So it has periodic condition, like in both ploidal and the toroidal directions.
That form of delta W implies fixed boundary. That's the simplest form. Then if you have a gap between the plasma and the wall, then you can surface distortions and continue going into the gap, and it makes for more of a slot.
Okay, thank you. So because the line bending means K parallel not equal to 0, right? If K parallel is equal to 0, the field line is still straight, because let's say, I will talk about it later, but I can explain to you very briefly, because in plasma, especially in ideal plasma, there's a law called flux freezing law, which means the magnetic field can move together with fluids. So if there is a perturbation, you can see the oscillation. Because the moment of the field line are coupled to the moment of fluids, when the fluid moves, the field line will also move together. So there will be bending of the magnetic field lines, which cost you extra energy, because here the first term is proportional to K parallel squared. So if the field line is bended, it will stabilize the plasma mode. Oh yeah, the takeaway is on resonant surfaces, the K parallel, the parallel wave number of the plus mode is equal to 0, which means on resonant surface, the field line is not bended, which is energetically favorable. So at resonant surfaces, it's easy to get to excite plasma modes because you don't bend the magnetic field lines. And also it can also minimize the Landau damping. This is another, this is a takeaway. Okay. So after this long introduction, you may wonder what happens if the magnetic shear is present, because magnetic shear is present in tokamaks. So what are the effects of magnetic shear on modes? So here I will start with the simplest mode, which is interchange mode, which means the heavy fluid just pressing on the light fluid. So in the case of no shear, no resistivity, the plasma tend to perfectly align with the field line, which means the K parallel is equal to 0. So as shown in this picture, the plasma mode is invariant along the main field line, which look like the fluid in the ancient Greek buildings. So it gets another name, fluid instability. So this equation, just the ideal MHD equations, and by simple algebra, we can get the eigenmode equation. And finally, it yields the growth rate of the mode. As we can see in this growth rate is proportional to ky squared and inversely proportional to k perp squared. So it favors small kx and large ky. So this mode with small kx and large ky has very large growth rate. So as shown in this picture, mode with very long extent in the radial direction is favorable, and it can, at the same time, it also alternates very quickly in the y direction. So this kind of modes are efficient for the radial transport. However, what happens when magnetic shear is present? So mode always wants to align with the field line because it doesn't want to bend the field line to cause energy. At the same time, when magnetic shear is present, field lines are twisted in space. So it means when deviate from the resonant surface, magnetic field pinch changes, and the mode pitch and the magnetic pitch can no longer match, which means when you move away from the resonant surface, the K parallel is no longer equal to 0. Mathematically, you can calculate the K parallel with the presence of magnetic shear. You can see it's proportional to x. X is the distance from the resonant surface in the radial direction. So with the presence of magnetic shear, K parallel can only be 0 at the resonant surfaces, and the K parallel increases with x. So as I just introduced, the K parallel not equal to 0 means the field line indicates field line bending, which is energetically unfavorable. So when the field line is bended, this effect can stabilize the mode. So that's why we have the Sweet-Damped criterion, which basically say there is a critical pressure gradient. So beyond which we can have instability, but below which we don't have instability because of the stabilization of the line bending effect. So and another thing indicated by this equation is that the farther away from the resonant surface, the stronger the line bending effect because the K parallel is larger. Remember, the first term in energy principle is proportional to K parallel squared. So the farther away from the resonant surface, the stronger the line bending impact. This indicates the mode will be localized with the vertical direction. When localized, but localized. Here is simple cartoon. The light is bad because you cannot see the plasma filaments here, but here I use a simple cartoon to illustrate why the magnetic the flux floating law can lead to field line bending and lead to the stabilization. So you can think of the magnetic field line as a string, right? Because just like the Kelvin theorem, in the fluid mechanics, vorticity through any given moving fluid element does not change. In plasma, in plasma physics, if the plasma is ideal, the magnetic flux through any given moving flux element does not change. So think of the magnetic field as a string. If there is perturbation, the field line will move together with the plasma, which leads to the field line bending and the stabilization. Just as the Kelvin theorem is broken by viscosity, in plasma physics, the flux-Roving law is also is broken by the resistivity. So with fine resistivity, plasma can detach from the field line. So previously, the plasma moved together with the field line moved together with the plasma. Suddenly, the plasma detached from the field line, and the straight field line recover. We can the stability can continue. So here the key point is even very small plasma resistivity can lead to n-trivial results. Because look, here is the conduction equation. If you compare the first term and the last term, you will see this term will dominate, even though the E is very small, because the first term is proportional to K parallel at a resonant surface. The K parallel is equal to 0. So even if the eta is very small, this term can still dominate at near the resonant surfaces. So resistivity can make interchange mode get access to the energy again. Mm-hmm. Yeah. Okay. So if we consider resistivity, we will translate from the ideal MHD to resistive MHD. Basically, we just change the Ohm's law and finally get this eigen equation for the resistive interchange mode. As we can see here, the Lundquist number, which is the ratio of resistive fusion time to the Alpha time, very large. But since as I just said, the resistivity still has a non-trivial effect. And here the mode is very here the growth rate is proportional to eta to 1/3, and the mode width is also is proportional to 1/s to 1/3, which means the most structure is very narrow and localized at resonant surfaces. So here I can draw the conclusion modes are pinned at the resonant surfaces. I will show later this localized modes could be a possible mechanism, alternative mechanism account for the avalanche. So here comes the first advertisement. I mean, this is my own work. I study how the stochastic magnetic field affects the resistive interchange. Here, in my previous introduction, the magnetic field is regular and smooth. But however, in tokamak, when two magnetic islands overlap in the overlapping area, the stochastic field line, the field lines will become stochastic, which means two infinitely closed field line will diverge in space very quickly or exponentially. So we would like to ask, how does this stochastic magnetic field modify the dynamics of a single interchange mode? This question is motivated by the adoption of a technique called resonant magnetic perturbation in tokamaks. So basically, the conclusion is, since the plasma can flow along the stochastic magnetic field, it will generate a non-trivial current density fluctuation. So to maintain the quasi neutrality, the deep J equals 0, the plasma needs to respond to this this J-twin parallel. So the response is small scale convective cells are driven, which provides another current density fluctuation J2 parallel perp, which balances the J-twin parallel, so that the total current density fluctuation is divergence free. We can prove there is a non-zero correlation between this microturbulence and the stochastic magnetic field. And the stochastic magnetic field can enhance the effective plasma inertia and thus slow down the mode growth. Okay, so after talking about the resistive interchange, it's good time to look at its wave packet because since the resistive interchange mode are still narrow, they are localized at resonant surfaces, they are not efficient, they are not effective for mixing because it's narrow. But if you look at the wave packet of this resistive interchange mode, we can see it has a much broader mode structure, which is efficient for mixing. And another this wave packet is called quasi-mode, the first introduced by Roberts and Taylor in their paper. And another purpose of the introduction of quasi-mode is it's a natural connect. It can connect to the ballooning mode. I mean, it has a very similar mode structure to the ballooning mode, and naturally serves as a bridge from the cylindrical world to the toroidal world. The reason why we want to study ballooning is also simple because it's very important. It's a very possible candidate for the cross of the age localized mode, which can lead to severe damage to the first of the tokamak. But there is very mature studies on the linear theory of a ballooning mode. But if you want to study something more complicated, for example, how stochastic magnetic field affects the ballooning mode, especially in tokamak, it could be simpler, but in the stellarator, doing a direct study is very difficult. So if we can study quasi-mode first, and we can get some useful physical insights for us to study the ballooning mode. Okay, here is quasi-mode. It's the basic of the quasi-mode. It's, as I said, it's just a wave packet, a radially localized interchange mode, as shown in this picture. The yellow columns in this direction is just the plasma filaments, and this is the convective cell of the resistive interchange mode. And the red envelope curve is just the convective cell of the quasi-mode. As we can see, it's very broad in the vertical direction, so it's efficient for mixing. As indicated by its name, it's a wave packet, so which means it's not an eigenmode, right? So for wave packet, its eventual destiny is to disperse, right? But since these resistive interchange modes are highly degenerated, this quasi-mode has very long lifetime. It can maintain its shape until it enters a nonlinear phase in which the linear theory breaks down. So, and this picture is just a project of this picture in the XY plane. So this is a if there's no shear, the convective cell should look like this. It's vertical. But however, if the max shear is present, when you move along the mean field line, you can see this convective cell should twist. And so that's why it has another name, twisted slicing mode. So this is a basic setup of quasi-mode. I will just skip, and this is the equation of the quasi-mode, and finally we get the eigenmode, the mode equation for the quasi-mode. And here you can see there is a familiar operator B dot grad. The question is how to simplify this operator to simplify the calculation. We can use there's a useful tool called twisted slicing coordinates. Basically, you can do this transformation, and the derivative operator should be rewritten correspondingly. And after this transformation, we'll see the B even though there's magnetic shear, the B dot grad can be rewritten into this simple form in which the shearing term is removed. So this is a very useful tool. So after taking this transformation, we can finally get this equation. It's still very complicated, but by adopting by taking some limits, we can eliminate many of them and get a very simple equation. You can think of this geometry as a periodical cylinder or slab. And as I just skip because it's bounded in the vertical direction, but it's open or unbounded in the ploidal and the toroidal direction. I mean, so the magnetic shear, the magnetic field lines has shear in the vertical direction. So you can see the field line is just, for example, this field line in this direction, and this field line in this direction, and this field line in that direction. So it has a shear in the vertical direction. So the plasma filaments need to, since the plasma filament tend to align with the field line, it has to, it has to have different the directions in at different head. So this is the effect of the magnetic shear. Here, the effective gravity, which is just Y and Z, right? Because the magnetic field is in the Z direction, the mean magnetic field in Z direction. That's the, yeah, because here the magnetic shear is very weak, right? So and the sheared magnetic field is in the Y direction, but the mean magnetic field is uniform in the Z direction. So, yeah, very strong. Yeah. Yes. So this is the strong mean magnetic field in the Z direction makes the system anisotropy. Yeah. So this is the equation we finally get. As you can see, it has a structure similar to the harmonic oscillator in the quantum mechanics. Well, you can see. I mean, the equation for the oh yeah, the equation for the resistive interchange mode is also a harmonic oscillator. So here we get another one. But this is, I should clarify, this is not a coincidence because after the twist transformation, the zeta corresponds to the length, this coordinate along the mean field line. Since the key parallel and zeta are conjugate variables and key parallel is proportional to x, so zeta and x are also conjugate variables. So if you have a harmonic oscillator with respect to x, then naturally you will have another harmonic oscillator with respect to zeta. So this is why we get another harmonic oscillator. And here we have the solution to this equation, which is analytically doable. And this is the picture for the mode structure of the quasi-mode. This is magnetic field lines, and the arrows mark the local velocity field. The color, the blue and red, just denotes the rising and the falling motion of the plasma, and the color just denote the magnitude of the mode. If you look at this mode in the XY plane, you can see this convective cells are twisted compared to the vertical plane of the ideal interchange mode. So as indicated by this solution, and also in this picture, the quasi-mode has finite length in the mean field direction compared to the resistive interchange mode. If you, because the system is open in the Y and the Z direction, the resistive interchange mode has infinite length in the Z direction. However, in this case, the quasi-mode has finite length in Z direction. Here, I can explain it algebra, but here I can also explain in the more physical way, because when there is a magnetic shear, when the plasma filaments are denoted by the yellow columns in this picture, as the plasma filaments move up or down, in order to keep alignment with the magnetic field, it needs to rotate as moving up and down. This is the top view of this picture, and the yellow this yellow column is just corresponds to the yellow column in this bigger picture. It's just the convective plasma filaments. As it move up and down, it will rotate with respect to the x-axis. So if the system if the quasi-mode has perfect alignment with the field line, it needs to have the infinite length in the z direction, because the system is infinite in the z direction, which means the rotational kinetic energy will diverge because of its infinite length. However, but this is not physical, right? So the mode has to adjust to a finite mode length to reduce rotational kinetic energy, which at the same time also indicates plasma cannot perfectly align with the field line. So plasma needs to detach from the field line due to the resistivity. The detachment of the plasma from the field line can enhance the resist dissipation. So finally, the mode length along the mean field line is determined by the balance among the gravitational potential energy released by the plasma motion and the rotational kinetic energy and the dissipative energy. So yeah, this energy budget determines the mode structure and mode length. We can explicitly show that the quasi-mode in a linear superposition with its interchange mode. This is the solution to this is the eigenmode for the resist interchange. If we take the integral over them, we can finally get the expression for the quasi-mode, which is exactly same as what we have previously. So this picture just showed me this small circular convective cells that just correspond with the interchange, and this is just the quasi-mode. Okay, here comes the second advertisement. Yeah, because as I just said, I mean, the resist interchange mode are localized near resonance surfaces, so they are not efficient for mixing because the step size is very small. However, if you look at wave packet, the superposition interchange mode, resist interchange mode, the quasi-mode has very broad structure in the radial direction, which means the step size is much larger, so it's very efficient for the mixing. So that's why the quasi-mode is important. So here comes the second advertisement, the how stochastic magnetic field modify the quasi-mode. Yeah, later I will discuss how ballooning mode is related to quasi-mode. And I mean, since the quasi-mode is just wave packet of the resist interchange, I mean, we can expect similar results because it's just a linear superposition of the resist interchange. However, since there's a change in the mode structure, we also expect something should change. But here is a main results. I mean, because we still have the emergence of the small scale convective cells. However, we can see because of the change in the mode structure, the stabilization of the quasi-mode is much stronger for compared to the resist interchange, and the turbulence damping is stronger, and the B twiddle Y we twiddle correlation enters our system, which is also non-zero. All of these changes can be attributed to the change in mode structure and the spatial ordering. Okay, so after the introduction, of the quasi-mode, I think, and a short advertisement, I think it's a good time to go to the world of the torus. Because previously I just said the periodic cylinder is produced because you cut the torus and straighten it. However, here you can think you bend the cylinder and connect these two ends and to form a torus. Because this torus has a curvature, the mean field line is bended, so there will be when the plasma moving along the field line, it will you can feel a centrifugal force which can be renormalized as the effective gravity. So the ploidal symmetry of this system is broken in the toroidal configuration because in the outer side the curvature is in the same direction as the pressure gradient, but in the inner side, these two things have opposite directions. So the inner side is a good curvature regime, and the outer side is the bad curvature regime. So why should I? So as I said, another purpose of introducing quasi-mode is because it has very similar mode structure as the ballooning mode. These localized ploidal harmonics are coupled due to this toroidicity effect to form a ballooning mode. And as I said, quasi-mode is just real packet of localized resistive interchange. So they are both composed of localized modes, and they are both rolled in the radial or vertical direction. So they are very similar. The difference is the ballooning mode is an eigenmode, and the quasi-mode is a wave packet. So it's not an eigenmode. So a quasi-mode in a cylinder resembles a ballooning mode in a torus. To study ballooning mode, there are two conventional methods. We have block eigenmode equation and the ballooning mode representation. So in this talk, I will briefly introduce them. So because of, as I just said, because the magnetic field has a curvature due to the shape of torus, the plasma will undergo a curvature drift and the grad B drift, whose expression is given here. As shown in this picture, this is the direction of the curvature, and this is the direction of the magnetic field. And this red arrow denotes the direction of the drift. It has two components. One is in the radial direction, one is in the ploidal direction. And this drift will enter the ion continuity equation in which you can derive the Hasegawa-Mimma equation. So as we can see, because due to the toroidicity, there is a drift, and this drift is dependent on the ploidal angle theta. So this drift will couple the modes with different ploidal mode number. So we have this equation which coupled phi m and phi m minus -1, phi m plus 1. So the mode is coupled with its adjacent modes. We can simplify that equation. We can rewrite it in a more compact form, which is very similar to the 1D linear harmonic oscillator chain. So we can solve them analytically, and so the problem reduces the block eigenmode problem in the condensed matter physics, in which we solve the wave function in the periodic potential. One thing I need to emphasize is that toroidicity introduces a new scale, delta R, which is the spacing between two adjacent harmonics. After a simple calculation, its expression is given here. It's inversely proportional to the Ky. So if Ky is large, the spacing between two adjacent ploidal harmonics is very small. So we can assume the adjacent harmonics have the same shape. So we can relate the phi m minus 1, phi m plus 1 to phi m. So this equation is simplified to this following equation. We can say phi m is the only unknown function, but there is also spatial translation in this equation. So to deal with this spatial translation, we can take the Fourier transform with respect to x. So we can have this eigenmode equation. I need to emphasize again, since eta here is the distance along the mean field line is conjugated to k parallel, which is proportional to x. So if we solve this equation, we can get the mode structure along the field line. If we take the inverse transformation, we can get the mode structure in the radial direction. If we compare the mode structure, if can compare the radial extent of the toroidal harmonics to the spacing between them, we can define the strong ballooning and weak ballooning regime. So this above is the block eigenmode equation formalism. Here comes another approach, which is called a ballooning mode representation. So for ballooning mode, it has very slowly in the parallel direction compared to the perpendicular direction. So K perp is much larger than K parallel. In such slowly varying medium, it's naturally to write any perturbation into an akinal form. So that's why we have this formula. I should say this is not only applicable to ballooning mode, but also applicable to many other modes who own these properties, which is quite Euro. But however, this expression is not correct to describe the ballooning mode because it doesn't fit the toroidal periodicity requirement. For example, if here we assume f is a very slowly varying function. So if f I equals 0 is equal to f I equal to 2 pi at one specific radial position, then it can be proved that this condition is no longer satisfied in another radial position unless you say f is not a slowly varying function. So we need to think of a way to reconcile the requirement of the toroidal periodicity and the akinal form. So this leads us to the ballooning mode representation. So the basic idea is if the phi hat is a solution of the 2D eigenvalue problem of this equation here, the eta is no longer the toroidal theta, is the extended toroidal angle, or you can interpret it as the distance along the mean field coordinate. Then if phi hat is a solution of this equation, then we can say the phi theta x, which is related to phi hat through this equation, is also a periodic eigensolution for this eigenfunction. So I just skip the proof; it's just trivial. But so after doing this, after replacing the theta by eta, it's safe now. It's safe to write the perturbation into this akinal form, and the phi theta, the expression for theta is just given here. Since m minus nq is just the k parallel, so the eta is just the distance along the mean field line. We recall the expression for the Quasimodo. I hope this can answer Guillaume's question. And we recall the expression for the Quasimodo. This akinal form of phi hat is in the similar similar form as the Quasimodo. So if you take the simple algebra, we can see the ballooning mode is just a superposition of infinite number of Quasimodes, and it can also be shown that the ballooning mode is a superposition of localized ploidal harmonics at different resonant surfaces as shown in this picture. Okay, so we have finished the linear part of my talk. So many of you may get tired of one linear mode after another. So here I'd like to introduce something more interesting, which is the nonlinear effect. So first thing I'd like to introduce the magnetic shear enhanced decorrelation. So here is the equation for the magnetic flux. According to the definition of the magnetic flux, it should be invariant along the field line. So B dot grad phi is equal to 0. But when there is a stochastic magnetic field, if we rewrite this equation into a more detailed form, we can see that there is a term involving B twiddle R. I mean, this is just like the quasi-linear equation. The system needs to give a response to this stochastic magnetic field, so we can decompose the phi into psi into psi bar and psi twiddle, and we can get the linear response of psi twiddle to B twiddle. And finally, this stochastic bending term in the equation can be renormalized as the diffusion term in the evolution equation for the mean magnetic field. So, and the dm here is just the magnetic diffusivity. We can adopt the twisted Satin coordinates to simplify this equation. So after transformation, this magnetic shear for a shear term is eliminated, and we can see the psi bar is proportional to e to minus z squared, z cubed. So this means the stochastic bending can lead to enhanced decorrelation of the magnetic field. So based on this exponent, we can define a decorrelation length whose expression is given here. It just means if two magnetic fields are infinitely close at the beginning, then when these two fields move along the mean field line, it will diverge exponentially and becomes decorrelated. For electron, if we divide this length by this thermal velocity, we can define the decorrelation time as well. Another thing I want to talk about is how geometry affects nonlinear coupling. This is a very interesting topic because frequently in theories, in many theories, we can meet this operator B twiddle grad V twiddle, which is the stochastic bending term. If you calculate, this term, inside this term, there is a coupling effect, which is theta dot k perp prime cross k perp. Right? So if we want to determine the coupling, the nonlinear coupling between these two modes, between two modes, we need to evaluate the coupling factor, which is this. So by doing a simple calculation, we can see for resistive interchange mode, this coupling factor is not equal to 0. However, for quasi mode, due to the change in the mode structure, this coupling factor is equal to 0, which this means the coupling factor between two wave packages is 0. So recall the saturation mechanism of a mode in tokamak. So a mode can only saturate mainly by two approaches. First, it can transfer energy to other modes, just like think of the turbulence. There's a cascade of energy between different scales, and finally it will dissipate at a Kolmogorov scale. And another scheme is the mode cannot transfer energy to other scales, to other modes, so it will use up the free energy and lead to it can feedback on the mean profile evolution. So since the mode coupling between wave package or quasi mode is 0 according to our calculation, so there's no energy transfer between the quasi modes, so can only feedback on the mean gradient. So for example, in the end, the quasi mode will relax to near marginality, and perhaps we will see the plateau formation in the density profile. So if we look at the mean mean electrostatic potential evolution, we may find the zonal mode. So, but for ballooning mode, as we can see, the scene is even more subtle, because if we calculate the coupling factor, which is calculated by Freeman and Chen in their nonlinear gyrokinetics paper, we can see this coupling factor is proportional to this integral. You may ask, what is eta n prime and eta n? They are the coordinates. N and n prime denotes two different ballooning modes. Okay, so eta n and eta n prime are the coordinates along the mean field line of these two different modes. So if we treat this partial nu over partial x as a constant, we can move it out of this integral. We can see the c is proportional to the difference between eta n prime and eta n. However, so we may say, okay, then there is a non-trivial coupling between the ballooning mode, right? However, since the ballooning effect is the strongest near the outer mid-plane, if all the ballooning modes are concentrated in the outer mid-plane, then the eta n and the eta n prime will be very close, which means the coupling between these two ballooning modes is very weak. So here we have a competition between the mode stability and the nonlinear coupling. Similar as the quasi mode, since the coupling is very weak, so finally we will have a feedback on the mean gradient. But this picture can give us some indication for avalanche, right? I mean, there are many visualizations of avalanche and many analysis on this topic, but I think the basic picture, I mean, the mechanism of an avalanche is still an open question. But here we provide alternative pictures for the happening of avalanche. So there are two ways to have avalanche. First, here we have very localized, very spatially localized modes. They overlap in space. So if we excite one, then due to their overlapping, this excitation will transfer to the other mode, which is the avalanche. This spatially localized mode can couple either due to the ballooning effect, or you can just think of the wave packet. I mean, maybe the avalanche could just be a wave packet, but with this interchange mode. And this picture is quite similar to the traditional sand pile model, because here the width of the narrow localized mode is very small compared to the minor radius, just like the unit size of this sand pile is much smaller than the box size. However, there is another possibility, because as I just showed, there is a non-trivial, maybe weak, but there's a non-trivial interaction between the ballooning mode. So instead of having spatially localized modes overlapping each other, we can have the interaction between a broader ballooning mode. So you have these several steps. We can have maybe 2 or 3 steps to achieve the avalanche. So here we have 2 ways to have avalanche, but I mean, due to the lack of analysis, which one is the criminal still remains unclear. So here comes the summary. In this talk, we explain how the geometry affects turbulence, instability, and transport. In the periodical cylinder, I show when the field pitch equals mode pitch, we can define resonant surfaces, which is ideal habitat for instability. However, the magnetic shear can stabilize and localize the mode. Regarding the nonlinear effect of the magnetic shear, it can lead to the enhanced correlation. And then resistivity can detach the fluids from the fields which restore the instability. But now the instability is still very narrow. But here, if we look at the wave packet of this spatial localized instability, we can get a quasi mode which has a much broader mode structure. This is good for mixing, and And but at the same time, it's the mode coupling between these two wave packets is managed, and from this wave packet we can naturally connect to the ballooning mode, which is in the toroidal geometry. The ballooning mode is just coupling of fluidal harmonics, and I introduced two conventional methods: block eigenmode equation and the ballooning mode representation. And I show that the nonlinear coupling between the ballooning mode has a competition with the mode stability. The nonlinear coupling of the ballooning mode provides an alternative picture for the avalanche, which means the step size could be much larger compared to the picture of overlapping localized mode. So, what's the time?
Unless people want to buy you one.
Yeah. Okay. Yeah. I mean, here I just want to tell you a sad story of the velocity shear, because if you look carefully, the magnetic shear and the velocity shear has very similar structure. So the technique we use for the magnetic shear is also applicable to the velocity shear. We can use the shearing coordinate, which is proposed by the Goldwich and the Bell. We can eliminate the velocity shear term and to simplify the calculation. Similar to the magnetic shear enhanced correlation, we have the velocity shear enhanced correlation. We can which basically has the same result. We can define the decorrelation time. That's it.